Hello everyone, this is Dr. Lennon, and in section 7.2 we're going to be looking at partial derivatives for these multivariable functions. So when we had single variable functions, when we took the derivative, we would treat one as the input value and one as the output value, and we followed the according derivative rules. Here we've got an output value and two input values in terms of variables. So what we're going to do is we're going to develop partial derivatives. So we're not going to focus too much on the theory of developing, but the main idea is that when you take the partial derivative, you're picking one of the input variables, and you're only treating that as the variable, and you're treating everything else as the constant. So if you have a variable with respect to x and y, and you're taking the partial derivative with respect to x, then you're going to treat the y variable as a constant, and you're going to be thinking about the functions only in terms of x. So let's go ahead and look at the first few examples in the PowerPoint, and then we'll go ahead and do some additional ones. So 7.2 partial derivatives. Again, they have some notation here. A lot of times what we have when we're taking the partial derivative of the function, we will use a subscript to denote it. So there's kind of two ways. There's the typical notation and also the Leibniz notation. So if we have a function, so suppose, let's say suppose z equals f of x, y is a differentiable function. Then the notation for the partial derivative of f with respect to x, and it'll be analogous for y, is, so there's two ways to write it. So we could either write it as f with a subscripted x, or we could write something similar to the Leibniz notation where we have this symbol. It's a del. It kind of looks like a curvy D, and it would be del f or del z, depending on what you want, del x. So where D is the derivative operator. So analogously, sorry, I spelled that wrong. Analogously, that's still wrong. There needs to be an O in there. Sorry. Analogously, fy is the partial with respect to y. And here we could do the same thing. We could say analogously. Gosh, I'm having trouble writing today. So here what we'd do, we'd write del f, del y like this. Okay, so those are the two ways that you can write the partial derivatives. Let's go back. And basically they're saying if you have this two variable function, you just take the derivative with respect to x to find the partial with respect to x. So you can write this out in terms of limits. Now your limits are two variable limits where you're just moving x in the x direction, y in the y direction. Again, we're not going to focus on the theory too much. Since this is an applied class, we're just going to focus on the implementation and finding some of these partial derivatives. Okay, so let's go ahead and move on. Okay, so in this example, they want you to find the partial differential, the partial derivative with respect to x, and then plug in 2, 1, and then the partial derivative with respect to y and plug in 2, 1. So if we look at this function right here, x cubed plus x squared y cubed minus 2y squared, if we were going to take the derivative with respect to x, you're going to treat all the y components as constant. So if we look at the partial derivative with respect to x, we would expect the derivative of x cubed to be 3x squared. And then when you look at the second term, rather than taking the derivative of x squared and y cubed and doing a product rule or something like that, we're thinking of y cubed as constant. So we just say, okay, how do we do the derivative of x squared, which is 2x, and then we multiply that by y cubed. And then the last term, minus 2y squared, has no x factor whatsoever. So the derivative of 2y squared is just going to be 0. So if we looked at the x partial derivative of f of xy, we would get 3x squared plus 2xy cubed. And then that result we would plug in. So they're doing this kind of in a funny way. They're plugging in the y variable to get a single variable function. Then they're going ahead and doing the derivative just with respect to x. I was doing it by just taking the partial derivative immediately. So let's look at this alternative way where we take partial derivatives immediately. So let's move back to the notes. So let's say example. So let's remind ourselves of what the function was. Suppose f of xy is, or let's say equals. Gosh, I'm making all kinds of weird mistakes. F of xy equals, I think what we have, x cubed plus x squared y cubed minus 2y squared, I believe was the function. Let's go back and check. X cubed, x squared y, yeah, minus 2y squared. And then we're plugging into 1. Okay, so let's say first find the partial derivative with respect to x. So here, basically, fx of xy, like I said, the derivative of x cubed would be 3x squared, and then the derivative of the x squared y cubed, we would have 2x times y cubed, and then the last minus 2y squared vanishes, so we just get that as the partial derivative. B, we could also get the partial derivative with respect to y. So now you do the same thing, but we're treating y as the variable rather than x. So we have fy of x comma y. This is going to be, well, now the first term doesn't have any y's in it, so the derivative of x cubed with respect to y is going to be 0. When we're looking at the middle term, x squared y cubed, we just want to think about taking the derivative of y cubed, which would be 3y squared. So we would get 3x squared y squared, just leaving the x squared alone. And then the derivative of y squared would be 2y, so the derivative of minus 2y squared would be minus 4y. And those are your two derivatives. So to plug in your points like they want, so let's say a prime, we want to find f sub x of 2 comma 1, we just plug in the point here into the formula. So replace x by 2, so we get 3 times 2 squared plus 3 times 2 times 1 cubed, and we end up with 12 plus 6, which gives us 20. And we can do the same thing for b. Let's say b prime, they want us to find f sub y of 2 comma 1. So now we move to this second partial derivative formula. So we would have 3 times 2 squared times 1 squared minus 4 times 1. So in this case we have 12 minus 4, which is 8. So that would be the value. So let's go back to the PowerPoint and see they did it a slightly different way by plugging in the variable that's unchanging first and then taking the derivative of that. So they end up with the same derivative, 3x squared plus 2x, plugging in 1, and then they get 16 for the first answer, and 8 for the second one. So let's just check back and... so I got 20 for the first one, 8 for the second one is correct. Did I do something wrong for the x partial derivative? I don't believe so. So let's see, 3 times 4 is 12. 12 plus 6 should be 18. Was that it? So I think I just added incorrectly. So it should be 18. And also, no, I made 2 mistakes. So somehow I transcribed a 3 here when it should have been a 2. So I wrote down the wrong number. So it should be plus 2 times 2 times 1 cubed. So now we get 12 plus 4, which is 16, which is the correct answer. So apologies there. Just some bad mental math on my part. Okay, so back to the slideshow. And again, we've got some notation for partial derivatives that we already kind of described. We see both things there. And now we'll just look at some partial derivative examples. So example 2 is just looking at example 1 through the lens that we did it. So notice our x partial derivative should be 3x squared plus 2xy cubed, which is exactly what we get. And then if we look at the y partial derivative, we should get 3x squared y squared minus 4y. So let's check and see that we get that. Yes, we get that also. So you get the same thing doing it that way. Okay, so here we have an interesting one. So notice that our basic function, so we have a function plugged into a function, right? We have x over 1 plus y, and then we're taking the 5th power of it. So we're going to have to use the chain rule here. So how do we do that? Let's go ahead and do this example the way that I typically write it down, and it might be differ a bit from the book because there's a number of ways to write down the chain rule. But let's go ahead and do this as well. So we have another example. So we have given f of xy is x over 1 plus y to the 5th power. We want to find the partial derivative with respect to x and the partial derivative with respect to y. So when we're doing the partial derivative with respect to x, let's write down our inside function. So our inside function is what's inside the parentheses, x over 1 plus y. And our outside function is just t to the 5th power. So we, again, remember, include another variable as a placeholder. And then we just take the derivatives as normal. So the outside prime, thinking of t as just a regular variable, would be 5t to the 4th. That's nothing too tricky there. The inside prime, we do have to remember that we're taking the derivative with respect to this part as a partial derivative with respect to x. So the only part concerning x is the numerator, and the derivative of x would just be 1. So the inside prime here is 1 over 1 plus y. And then we actually, okay, so sometimes you can include the input-output if you want for fx, so fx, x, comma, y. You could write it the same. Sometimes when we're abusing notation, we'll just write down f subscripted with x. All right, so how do we do the chain rule? Well, basically, we multiply the inside prime by the outside prime, and we then replace any occurrence by t with the original inside function. So this partial derivative with respect to x is going to be 1 over 1 plus y times 5, and then replace t by that inside x over 1 plus y in parentheses raised to the 4th power. So we could simplify this a bit if we want. So we would have 1 over 1 plus y times our 5 times x to the 4th over 1 plus y to the 4th, applying a law of exponents there. And then we could multiply all this together to get 5x to the 4th divided by 1 plus y to the 5th power. And that would be our partial derivative with respect to x. So if we're doing the partial derivative with respect to y, so part B, if we're trying to find fy of x comma y, we're going to end up with the same inside and outside functions, but the only difference is going to be the choice for finding the derivative of the inside. So the inside here we have x over 1 plus y, and then the outside again is still just t to the 5th. So the outside prime is easy to figure out. This comes out to 5t to the 4th. And then the inside prime here, well, what do we have? We're going to have to use either a chain rule or a quotient rule, depending upon how we think about this. I would prefer a chain rule myself. So if I'm doing the chain rule, I would write this as x. So let's kind of work off to the side here and say chain rule to find n prime. And this is kind of just like scratch work to help us with the rest of the problem. So how does that work? Well, we want to say x over 1 plus y. This is the same thing as x times 1 plus y to the negative 1st power. So then your inside function here is just 1 plus y, and your outside function would be x times t to the negative 1, where we're treating t as our variable, and x is a constant. So the inside prime here would just be 1, and the outside prime would be negative x t to the negative 2nd. So our derivative for the inside would come out to be, again, you do in prime times out prime. So we just have negative x, and then we want to replace t with 1 plus y to the negative 2nd power. So that's how we get our n prime. You could also use the quotient rule if you want. It's purely preference. Okay, so to find the partial derivative with respect to y, here we are going to multiply inside prime by outside prime. So we have negative x. Instead of 1 plus y to the negative 2nd, now I'm going to write it as 1 plus y to the 2, but in the denominator, times 5. And then we have times our original inside. Change t back to x over 1 plus y to the 4th power. So this ends up as, we have negative 5x squared in the numerator, and then in the denominator we're going to have 1 plus y to the 6th power. So that is the derivative. So let's go back to the PowerPoint and see. They might write it a little bit differently, but hopefully they get the same answers. Less numbers to multiply in your head, so probably we have a higher chance of getting these correct. Again, okay, so we get the same thing for the partial derivative with respect to x. Now they want to use that exponent rule probably to make the middle term x to the 4th over quantity 1 plus y to the 4th, which they do, okay, and then they combine it, so they don't show that intermediate step. So we get the same. So let's scroll back up to partial with respect to x. We got the same answer. So now when we do the partial with respect to y, we're looking for minus 5x squared over 1 plus y to the 6th. So we see the partial with respect to y. They don't write out all the details, so I've got a little more detail in my examples, but we can see that they get the same answer. Negative 5x to the 5th over 1 plus y to the 6th. I forgot to raise that to the 4th power, I think. Yeah. So sorry. I made another error here. So geez, really messing things up today. So this is 5x to the 6th. Because this term in the line above should be times 5x to the 4th over 1 plus y to the 4th. So x times x to the 4th should be x to the 6th. I have no idea why I wrote down x squared. Sometimes when you're recording and doing these things, you're just not focused enough on the math. Okay, so let's go ahead and look at a few more examples that I have written down, and we'll see some further partial derivatives. So, example. Let's say find all first partial derivatives. Find all first. That way, if I change the name of the function, I don't have to rewrite the directions. So A, let's suppose we have f of xy equals x squared y squared times x to the fourth plus y to the fourth. Now, you could go ahead and do this problem as a chain rule problem if you want, but I think it's a bit easier to first rewrite the function. So let's expand the function, expand the formula to simplify the process. That way we don't have to use a product rule here. So basically we can rewrite f of xy and distribute the x squared y squared. So x squared y squared times x to the fourth is going to be x to the sixth y squared. And then the second term we're going to get x squared, and then y squared times y to the fourth is going to be y to the sixth. So now we can go ahead and take partial derivatives. So the partial derivative with respect to x of this formula, the derivative of x to the sixth is 6x to the fifth, so we get 6x to the fifth y squared, and then the derivative of x squared is 2x, so we get 2x y to the sixth. And then the partial derivative, again, treat x as a constant and take the derivative of y, so we'll get 2x to the sixth y plus 6x squared y to the fifth. In general, it's not wrong if you wrote it in a different order, but I generally like to go constants and then list my variables by alphabetical order. So I would have 6x squared y to the fifth. And those would be our two partial derivatives. Okay, so that's it for this example. Let's go ahead and do another one that will require the chain rule. So let's say B. Let's say we have g of xy equals, let's say x times the natural log of x squared plus y squared. So here we have, so let's do g of x. So first note that gx of xy, the partial with respect to x, will require a product rule because we have x times the natural log of the quantity x squared plus y squared. So we have x times a function of x. When we do the partial with respect to y, we will not have a product rule. So the derivative with respect to x will be a little bit more complex, or a little bit longer. So trying to find gx, we list u as x, and then v will be the natural log of x squared plus y squared. So we're actually going to need a chain rule. U prime is easy, that's just 1. V prime, so again, chain rule for v prime. We can kind of do this off to the side. We have the inside function as x squared plus y squared. My outside function I could write as the natural log of t. So then the inside prime is going to be 2x. Remember, y is treated as a constant, so y squared has derivative 0. And the outside prime is going to be 1 over t. So v prime here is going to be 2x times 1 over x squared plus y squared, which we can write as 2x over x squared plus y squared. So that's v prime, 2x over x squared plus y squared. So now for the product rule, again, we multiply u prime v plus uv prime. So my partial with respect to x here is going to be, again, these things can be Very messy, but you just kind of go ahead. So 1, we don't need to write that down. 1 times anything is just whatever that happens to be. So natural log of x squared plus y squared. And then we do plus x times 2x over x squared plus y squared. So x can be viewed as a fraction as x over 1. So we can simplify this to the natural log of x squared plus y squared times, plus 2x squared over x squared plus y squared. Okay, so that will be that. Again, this is kind of like scratch work for finding v prime. And then b, we want to do the same thing. Not b, we're just finding gy, excuse me. So finding gy, we just have a chain rule. So finding gy of xy only requires the chain rule. So we have our inside function as x squared plus y squared, and now our outside function is x times the natural log of t. So the derivative of the inside with respect to y is just going to be 2y. The derivative of the outside, thinking of t as our variable, is x times 1 over t. So our chain rule here, which is the derivative for so gy of xy, is, again, we do in prime times out prime. So we have 2y times x times 1 divided by x squared plus y squared. And I would write this as a single fraction as 2xy over x squared plus y squared. And again, I'm writing x before y in the numerator just because I prefer to write my variables in alphabetical order when they're multiplied together. Again, that's allowed because multiplication is commutative. So that is it for finding the partial derivative with respect to y. Okay, so hopefully that gives you some examples to work with, and if you have any other questions, let me know, and I am happy to answer them and do some more partial derivative examples. Really what you're doing is we're just remembering all our ideas from taking derivatives, but depending upon what the partial is, we think of one letter as a variable and all the other letters as constants. All right, this is Dr. Lennon signing off.